Hi everyone, welcome to Probability and Statistics. Module 1 is Foundations. Here we will cover counting, probability axioms, sample space, events, and Bayes theorem. What you will learn in this module is counting techniques using permutations and combinations, probability axioms, which are building blocks of probability theory, sample space and events, outcomes, events, and logic, conditional probability, dependency and independency of events, Bayes theorem, updating beliefs with evidence. Counting techniques. In counting techniques, we will see permutations where order matters, combinations where order is ignored. For example, if you are arranging R items from n distinct items, formula is probability of n r is equal to n factorial by n minus r factorial. For example, if you are going to set a PIN number for your ATM card, in how many ways you can set from 1 to 5 if the length of a allowed PIN is 3 digits. In that case, possible PIN numbers that can be selected from 1 to 5 with a length of 3 digits is probability of 5, 3 will be equal to 60 arrangements. So if you are given the numbers of 1, 2, 3, 4 and 5, and if you are asked to set a PIN number for your ATM card where the maximum length of PIN is 3 digits, in that case you can set your PIN in 60 ways. One more analogy is choosing a president, vice president, and a secretary for a committee from the possible committee members. Here, the order matters a lot, and each order or each arrangement is different from the other. Coming to combinations, for example, there are interested players from your class, and you are allowed to only select 11 members from the potential players for the final match. In that case, order doesn't matter whether the candidate is going to play the final match or not. That's it. That is choosing R items from N, and there is no regard to order. Formula for finding the combinations from N number of items, that is selecting R items, is equal to N factorial by R factorial into N minus R factorial. Example is how many 3-member committees can be formed from 5 people. That will be equal to CF phi 3 is equal to 10 committees, because CF phi 3 will be equal to 5 factorial by 2 factorial into 3 factorial. That will give 10 committees. Analogy, choosing a pizza topping combo. For example, when you are ordering a pizza, there can be multiple toppings available for selection. In that case, whether you choose paneer or cheese or corn or mushroom, the selection matters and the order doesn't matter. Ultimately, they are going to be present on your pizza, and the in which order you are selecting doesn't really matter in that case. Coming to a worked example for the counting principle is, let us take the problem of selecting a committee of 4 members from a group of experts where 6 are men and 5 are women. We're required to find the number of ways so that the committee includes at least 2 women members. So in a committee of 4, at least 2 members should be women, gender equality. Okay. This can be achieved in multiple ways. Case 1 or case A, where exactly 2 women are there in the committee. Case B, exactly 3 women are there. In case C, exactly 4 women are there. There is no other case because maximum allowed members are 4 in the committee. So there are three cases in which we can form a four-member committee, out of which at least two members are women. Let us see first case where exactly two women are there. These two women can be selected out of five possible members in CF 5-2 ways, and the remaining two members can be selected from the men. There are total 6 men, and two members need to be selected. That's why CF 6-2. Here we are multiplying CF 5-2 and CF 6-2 because both the processes are subpart of total process, that is selection of four-member committee. That's why we are multiplying. That is, task A needs to be performed, task B needs to be performed. That is, selection of women members, selection of male members needs to be completed. That's why we are multiplying. That will result in 150 ways. In case B, we are getting 60 ways. In case C, where exactly 4 women members are there, we can do it in CF 5, 4 ways. That is 5 ways. Thus, in total, we can select a committee of 4 members, where at least 2 are women in these ways. That is 150 plus 60 plus 5. In total, we can select such a committee with at least 2 women in 215 ways. Here, one important principle, that is multiplication principle, is there. If task A can be done in m ways, task B in n ways, together the tasks can be completed in m by n ways. That is, selection of women members, selection of male members, and the selection of committee. Now, probability axioms and sample space. Kolmogorov's axioms of probability. Axiom 1 is non-negativity. That is, probability of any event is always negative. That is, it can be 0 or positive. Normalization. That is second axiom, normalization. Probability of a sample space is equal to 1. The probability of entire sample space, that is probability of all the possible events in the random experiment, will be equal to 1. Additivity. If two events are mutually exclusive, that is, their intersection event probability is 0, in that case, probability of A union B is equal to probability of A plus probability of B. In words, we can say that the mutually exclusive events add up. Coming to sample space and events. Sample space represented by omega indicates a set of all possible outcomes in a random experiment. A random experiment is an experiment where the outcome is random and cannot be predicted beforehand. The sample space is set of all possible outcomes. Coming to examples, if you're tossing a coin, sample space will include heads and tails. In case of rolling a die, it will consist of 1, 2, 3, 4, 5, 6, because these are the possible faces that the die can show up. In case of tossing two coins, the sample space will consist of heads, 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 tail, tails, head, and tails, tails. Next, event. Event is any subset of the sample space. In case of rolling a even number, A is equal to 2, 4, 6. Getting at least one head when you are tossing two coins, it will be heads, heads, head, tail, tail, head, because at least one is head in this event. A simple event is an event where a single outcome is there. Now, complementary event. A complementary event of an event will consist of outcomes that are not in the actual event. That is, probability of A complement is equal to 1 minus probability of A. If probability of rain is 0.3, in that case, Probability of no rain will be 1 minus 0.3, which will be equal to 0.7. And union, A union B. Outcomes in A or B or both. Probability of A union B will be equal to probability of A plus probability of B minus probability of A intersection B. This is an example. Outcomes in case of intersection of two events, A intersection B. Outcomes in both A and B. If two events are exclusive, in that case, A intersection B equal to pi, and their probability is 0. Com Sorry, joint probability. Now and types of events. Key distinctions are, in case of mutually exclusive events, if you take two events which cannot occur simultaneously, for example, occurrence of a toss, in case of tossing a coin, occurrence of tails and heads are exclusive events. Independent events, occurrence of A doesn't affect B. For example, eating dosa by you is not at all impacted by the weather in USA. Both are independent events. And exhaustive events, together they cover entire sample space. For example, you are tossing a coin. Possible outcomes are heads and tails. Thus, these two events, that is, toss and getting tails and getting heads, are exhaustive events, equally likely. Each outcome has same probability. Now, let us take an event of rolling a dice. In that case, every face has an equal probability to turn up. Thus, those events are called equally likely events. Now, conditional probability and independence, which is very important. Conditional probability of two events, that is, probability of A given B. Here, the vertical line is called given. Probability of A given B is equal to probability of A given that B has already occurred. For example, what is the probability of going to a movie given it is raining? Probability of staying indoor given it is raining. Generally, probability of staying indoors is high given it is raining. Intuition is, we restrict our sample space B, then measure how much of B is also A. Example, a bag has 3 red, 2 blue balls. A ball is drawn without replacement. Find the probability of second ball being red given the first was red. After the first red ball was drawn, remaining are 2 red balls and 2 blue balls, that is 4 balls in total. And the probability of a second being red given the first is already red will be 2 by 4, because favorable cases, once the red ball is already drawn, is 2 by total balls 4, that will be 50%. Using formula, probability of A intersection B equal to probability of first red into probability second being red given first is red. That will be 3 by 5 into 2 by 4 is equal to 6 by 20, that will give 0.3. Here one important rule, that is multiplication rule, is there. Probability of A intersection B is equal to probability of B into probability of A given B, which is also equal to probability of A into probability of B given A. Bayes theorem. Sorry. Bayes theorem is all about updating beliefs. Probability of A given B is equal to probability of B given A into probability of A by probability of B, where probability of B is equal to sum of probability of B over all possible other events into probability of that particular event. Here we take prior. What is the probability of A? Your initial belief before seeing evidence. For example, probability of some people, certain people, 50% of people wearing black dress in a pub. Example, your initial belief before actually going into the after before entering the pub. Or in case of spam mails. Example, 1% of emails are spam. Probability of spam is equal to 0.01. Okay. Likelihood, probability B given A. Probability of evidence given hypothesis. Example, probability of word free given the mail is a spam will be 0.9. Now, posterior probability. Posterior probability is updating the belief after seeing the evidence. This is what Bayesian computation does. Analogy: a doctor updates disease probability after seeing test results. That is Bayes theorem. For example, let's take a classical medical test problem. A disease affects 1% of population, but once the patient goes for testing sensitivity is 95% and specificity is 90%. Patient tests positive. Find the probability that the patient has a disease given the test result is positive. Given probability of disease is 0.01 only, and the probability of positive given disease is 0.95. That is the sentence in the question, that is test sensitivity is equal to 0.9, sorry, 95% is represented by probability of a plus given D is equal to 0.95. Probability of a plus given D complement is equal to 0.10%. This is derived from specificity. Probability of a patient being affected by the disease is equal to probability of a positive given disease existence into probability of a disease plus probability of a positive given disease complement, that is no disease there, into probability of a person not getting impacted by the disease is equal to 0.95 into 0.01 plus 0.10 into 0.99. Thus, probability of a disease, probability of positive is equal to 0.0095 plus 0.099 will be equal to 0.1085. Thus, probability of disease given a positive result in the test will be equal to probability of a test result being positive in, sorry, given disease is already there, into probability of disease by probability of positive results. That will be equal to 0.95 into 0.01 by 0.1085. Thus, the final answer is probability of disease actually in the patient given positive result in the test will be equal to 0.0875. That is equal to 8.75%. Only 9% even with the positive test report. Thus, today's summary is we have discussed permutations, combinations, probability axioms, conditional probability, independent events, and Bayes theorem. In permutations, we have seen that order matters. Example is seating arrangement, and permutations of n r is equal to n factorial by n minus r factorial. And in case of combinations, order will be ignored. You can call it as selections, and C of n r is equal to n factorial by r factorial into n minus r factorial. In case of probability axioms, we have seen non-negativity. That is, probability of any event will be non-negative.
It can be 0 or positive value. And in case of normalization, the probability of sample space will be equal to 1. That is, probability of is set with all possible events will be equal to 1. Additivity, in case of exclusive events, the probability of both the events together will be equal to sum of individual probabilities. And conditional probability of A given B is equal to probability of A intersection B by probability of B. Here we are restricting the sample space. Independent events, probability of A intersection B will be equal to probability of A into probability of B because of no influence of each event on the other. In case of Bayes theorem, we are updating our beliefs. Probability of A given B equal to probability of B given A into probability of A by probability of B. It is posterior update. Thank you. We will meet in the next session.